Hello everyone, this is Professor Roman. Welcome to the 16th video in my video lecture series, An Introduction to Discrete Mathematics. In this video, we are going to discuss equivalence relations in some detail. And let's begin with the definition. Let A be a non-empty set. A binary relation E on A that is reflexive, symmetric, and transitive is called an equivalence relation on A. And when A is related to B under an equivalence relation, we can say that A is equivalent to B, or because of symmetry, that A and B are equivalent. I'm going to denote the collection of all equivalence relations on A by EQU of A. Some simple examples. Logical equivalence is an equivalence relation. So is congruence mod K. Same length of vectors in the plane. Similarity of triangles. Same image under a function is an equivalence relation. Same truth table for logical circuits. There is a strong relationship between equivalence relations on a set and partitions of that set. So let's take a look at that. So let A be a non-empty set. Then any partition P of A, such as the one I've drawn here, defines what I'm going to call the same block relation and denote it by script E of P. So A is related to B under this relation if, by definition, A and B lie in the same block of the partition, hence the term same block relation. It's easy to see that this is reflexive, symmetric, and transitive. I'll leave the details to you. So we have an equivalence relation. Here's a simple example. If we partition the integers into two blocks, the even integers and the odd integers, then M is related to N under the same block equivalence relation, if and only if M and N are either together even or together odd. In other words, they have the same parity. Another way to say that is that M and N are related if 2 divides the difference, M minus N. So the same block equivalence relation here is just congruence mod 2. And you can generalize that to congruence mod 3 and to an arbitrary congruence modulo N. And I'll let you fill in the details should you be interested. The fact that every partition of a set leads to an equivalence relation is extremely important. In fact, all equivalence relations on a set A are same block equivalence relations for an appropriate partition. And before I show you what the partition is, we need another definition. Let E be an equivalence relation on a set A. For each element little a in capital A, that would be the underlying set, the equivalence class associated to little a is the set of all elements in the underlying set that are equivalent to A. And I'm going to also say that A generates this equivalence class or represents this equivalence class. Okay. The following theorem gives critical properties of equivalence classes. This may take a little while to get comfortable with. It's a bit abstract, so don't panic. It may take you a while to kind of get comfortable with this, as it does for, I would say, by far most of my students. Let E be an equivalence relation on a set A. then every element little a is in its own equivalence class. Little a is in the equivalence class generated by itself, by little a. That's pretty obvious because a is related to a. It's equivalent to a, and so it belongs to the equivalence class of a. What this also tells us is that all elements A belong to some equivalence class. Remember, we're trying to form this partition that I mentioned a minute ago. And it's going to be the distinct equivalence classes. So what we know so far is that every element of A belongs to an equivalence class, so the union of the equivalence classes is all of capital A. If little a and b belong to the underlying set, then their equivalence classes are equal if and only if they are equivalent. Another way to put that is that an element little b represents the equivalence class generated by A if and only if little b is contained in that equivalence class. Every element of the equivalence class represents that equivalence class. Finally, if A and B are elements of the underlying set, then the equivalence classes they generate are equal if and only if they're equal or they're disjoint. Okay. Two equivalence classes are equal or disjoint. Again, that's a property of the blocks of a partition. So the set of equivalence classes, the distinct equivalence classes, no duplicates, form a partition of the underlying set A. Let's go through the proof. Part A, I already discussed the proof. For part B, suppose first, so we're looking at this one. Suppose first that the equivalence classes of A and B are equal. Then little a belongs to the equivalence class generated by itself, which is also the equivalence class generated by B. So little a is in the equivalence class generated by B, which implies, by definition of equivalence class, that A is equivalent to B. And that is one direction of this biconditional. The other one is not much worse. If A is equivalent to B, then A belongs to the equivalence class generated by B. And if any other element belongs to the equivalence class generated by A, let's call that element X, then X is equivalent to A is equivalent to B, so transitivity tells us X is equivalent to B. In other words, X belongs to the equivalence class of B. So A equivalent to B implies this subset relation. Any X in here on the left side is also on the right side. It is also in the right side. But equivalence classes are symmetric. So A equivalent to B implies B is equivalent to A. And by interchanging the roles of A and B here, the equivalence class of B is contained in the equivalence class of A. But A equivalent to B tells us this. So we have both inclusions. So A equivalent to B implies the two equivalence classes are the same. For part C, that is this here, if two equivalence classes are not disjoint, they have an element X in common. Well, X is then equivalent to A. It's also equivalent to B. A little symmetry. A is equivalent to X, which is equivalent to B. Transitivity. gives us A equivalent to B. And by the previous part, we just proved the two equivalence classes are the same. So not disjoint means the same. So every pair of equivalence classes is either disjoint or the same. And when you tie all that together, it shows that this set of equivalence classes is a partition. So we can go from partitions to equivalence relations, the same block equivalence relation. We can go from equivalence relations to partitions, namely the set of all equivalence classes. And I'll have more to say about those two in a minute. It might help to cut down on some of the confusion here to keep in mind that there's a lot of duplication in the writing of equivalence classes. If I let little a range over the entire underlying set, and I write down all of these equivalence classes generated by all the elements of the underlying set, I'm going to be writing down the same equivalence class lots of times in general, because every element of this equivalence class generates this equivalence class. So I get, if an equivalence class has 10 elements in it, I'm going to get 10 copies of that equivalence class. Okay, but this expression here notes the brackets. This is a set. Sets aren't, you can't put duplicates in a set. So this is automatically deduplicated, right? This is the set of distinct equivalence classes. You know, if I were to write a curly brackets and write 1, 1, 2, you would say, no, you wrote 1 twice. You didn't mean to do that. Take one of those out. It's the same deal here with the equivalence classes. Identicality on a set. What are its equivalence classes? That's an equivalence relation, symmetric, reflexive, symmetric, and transitive. Well, the equivalence class generated by A is all the elements of the underlying set that are identical to A. Well, that's just A. So these are singleton subsets. So this set of equivalence classes, the partition, is in fact the finest possible partition on the set A, in the sense that each block just consists of a single element. You know, sometimes I find it helpful, and you may too, to think of a partition of a set as a sieve or a screen that sits over the set. And each block of the partition is like a hole in the sieve. The finest possible sieve is the one where each hole contains only a single element. The coarsest partition is the one block partition. The one block contains the entire set. Okay. Here's another example. Let A consist of all the straight lines in the plane. And let E be defined by specifying that line L1 is equivalent to line L2, I should say related to line L2, if and only if L1 is parallel to L2. Or in other words, L1 and L2 are parallel. I just gave it away. This is an equivalence relation. Okay. An equivalence class generated by a line L consists of the set of all lines that are parallel to L. So the equivalence classes essentially describe the directions in the plane, sets of parallel lines. Now we come to the most critical part of this whole discussion. How can we explain the importance of equivalence relations? Well, here's an example. Suppose that r square bracket x is the set of all formal real polynomials. So these are formal expressions. We've been through this before. 1 plus x and x plus 1 are different formal polynomial expressions. Equality is identicality. So these two polynomials are different as formal expressions. But suppose we want to eliminate this difference. In fact, more generally, suppose we want to ignore all the differences in formal polynomials that occur from the following three operations. Reordering the terms. I don't want that to be considered as producing a different object. It's going to be a different formal polynomial. Bear with me on this. I don't want two polynomials that differ only in the presence of terms with a zero coefficient to be considered different objects. I also don't want two polynomials that differ in that there may be two terms, like terms as they say, terms with the same power of x. Okay. I don't want that to be, I want to ignore that difference. Why would I want to do these things? Well, think about polynomials as functions. Reordering the terms doesn't change the function. It's the same function. 1 plus x and x plus 1 are the same function. You stick in a value for x, you get the same value out. Including zero coefficient terms doesn't change the value of the function, nor does separating terms into pieces like this, or combining these pieces. So from the point of view of functions, these differences are irrelevant. Well, this is exactly where equivalence relations come into play. We define a binary relation E on the formal polynomials by saying that P and Q are related, or P is related to Q, I guess I should say now, because we haven't shown this is an equivalence relation. If P can be converted to Q by one or more of these three operations, reordering the terms can change P into Q, adding or removing terms with the zero coefficient. So, whoops, forgot to remove it. Okay, so this polynomial and this polynomial, the only difference is that we, on the one hand, depending on which way you look at it, we added a term with coefficient 0 or we removed a term with coefficient 0. Okay. Adding or combining terms of the same like powers of x. So this is really replaced by 3x. Now, let me say this again. This is a binary relation. P is related to Q if you can turn P into Q by applying as many of these, finitely many of these as you want. And notice that I have deliberately used wording, adding or removing, adding or combining, so that these go in both directions. Because the operations can go in either direction, that's why I use double arrows here, this relation is symmetric. If you can convert P into Q, you can convert Q into P. It's clearly reflexive. You don't have to do any of these if you don't want to. So a polynomial is equivalent to itself, and it's transitive. So E is an equivalence relation on the formal polynomials. Moreover, two polynomials differ only in regard to these three. You can allow these three if and only if the two polynomials lie in the same equivalence class. In other words, if and only if they're equivalent. So it's the equivalence classes of E that are the objects of interest here, because we have removed these annoying possibilities of zero terms and reordering by squishing everything into equivalence classes. Well, we've got two choices really in practice. We can simply define a polynomial function as any formal polynomial, adding the caveat that two different formal polynomials may be the same polynomial function. Or we can define a polynomial function as an equivalence class under this equivalence relation. And both choices are useful. One of them is a little easier to cope with at first. The first choice here, just simply defining polynomial function as a formal polynomial where you can stick in values for x and out comes another value. So you can avoid mention of equivalence relations and equivalence classes and whatnot. But the downside, as I said, is the caveat that different formal polynomials can end up being the same function. And if somebody says to you, well, how does that happen? You're going to have to go through this whole thing we went through anyway. You're going to have to mention reordering the terms, adding or removing terms, adding or combining terms with like powers. So you're not really escaping a discussion of equivalence relations. You're just delaying it, or maybe hoping nobody will ask, So there's no free lunch here. The second choice is complicated by the fact that now polynomial functions are sets, they're equivalence classes. But the more comfortable you get with equivalence classes, the easier it is to cope with that, really. And it does have the advantage that distinct equivalence classes are distinct polynomial functions. So you don't have the ambiguity you had in the other case. Equality on the set of equivalence classes is identicality. That removes the annoyances that we have up here. I realize that's a bit abstract, and to be quite frank, you're not going to need this for the rest of the course. You will need equivalence classes, equivalence relations and equivalence classes and partitions, but not this detail of how equivalence relations are actually used in mathematics, because I don't think we're going to do this in sort of thing in this course. But it's done a lot in mathematics. In my course in linear algebra, I did it in order to define linear combinations properly, and I've done it in other situations as well. Okay, one more thing, and this is also a bit abstract, takes a while to get used to. We know that a partition P of a set A defines an equivalence relation, the same block equivalence relation. That gives us a function from the set of partitions of A to the set of equivalence relations on A. And I just realized that I used the same notation up here, so I'm going to simply say the set of equivalence classes. Okay. The function, script E here, sends a partition to the same block equivalence relation. This map is injective. If you have two distinct partitions, they can't have the same blocks. It's got to be at least a couple blocks different, so they'll have different same block equivalence relations. And that was a little sketchy, and I'm going to ask you, there's an exercise to make a little bit more formal argument for that. In the opposite direction, an equivalence relation E on an underlying set A defines a partition consisting of the distinct equivalence classes. So that gives us a function script P going from the equivalence relations to the partitions. This is nothing new, it's just a more elegant way of repeating what we've already done. This map is also injective because if two equivalence relations are different, they're not going to have the same equivalence classes, so their partitions will be different. Well, it happens that these two injective maps, E and P, are inverses of each other. In other words, this is where it gets a little tongue twisting. If you start with a partition and you form the same block equivalence relation, and then you take its equivalence classes, you get the blocks of P back again. If you start with an equivalence relation and you form its partition of equivalence classes, and then you look at the same block relation for those equivalence classes, you get the original equivalence relation back again. Okay? So I'm just going to prove one of these for you, and I'm going to let you handle the other one. So let me prove this one. To see that this is true, notice that if E is the same block equivalence relation for a partition, so you have a partition P, E is the same block equivalence relation. What are its equivalence classes? They're the blocks of P. Two elements are equivalent if and only if they're in the same block. So if you take an element little a, which equivalence class is it in? The set of all elements equivalent to A. In other words, the set of all elements in the same block as A. So I'm going to say it again. If E is the same block equivalence relation for a partition P, then the equivalence classes are the blocks. That's it, really. But change the symbols a little bit. Let E be script E of P. I said that E is, I should say, the same block equivalence relation for a partition P. So E is script E of P. The blocks of this equivalence class, the blocks of the corresponding partition of E are the blocks of P. So script P of this, those are the blocks of the partition, are the blocks of P. May have to think about this for a little while. This is devilishly abstract. Okay. In any case, this theorem is very important. It's something you really, if you want to do mathematics at some point or another, you will have to grapple with this. If you do, certain branches, if you want to be an applied mathematician and do differential equations and numerical analysis and so on, you may not ever need this. But in the softer types, abstract algebra, logic, and other places, this will be important. What it says, in essence, is that partitions and equivalence relations are simply two different ways of looking at the same concept. This is particularly useful in one direction, I think. Partitions are pretty simple, easy, intuitive concept. You just chop up a set into non-empty, non-overlapping blocks. But equivalence relations are less intuitive because they involve reflexivity, symmetry, transitivity. But what this theorem says is that we can pass back and forth between the two concepts, equivalence relation and partition. And there are times when we want to start with either one of these and decide that we're not making any headway. We should think, well, maybe we're looking at this from the wrong point of view. I have a partition, maybe we should be looking at the equivalence relation defined by the partition, the same block equivalence relation, or maybe I have an equivalence relation and I should be looking at that as a partition. I think that's probably the more common direction to go. Okay, but it's interesting that one of these two concepts, partition, is just so crystal clear. You can just picture in your mind a set and you chop it up and draw it on a piece of paper and chop it up into pieces. Equivalence relations are not so easy to picture, and yet there's no more information in an equivalence relation than there is in a partition. Okay, that's the end of this section, and so I'm going to stop the video. The next section is partially ordered sets. Thank you for watching, and I hope to see you in the next video.